Hi guys, this is Saptarshi here, and in today's session we are going to look at two important clustering algorithms, namely K-means and Hclust using R programming. You must have figured out that this is a hands-on session. However, no worries, we are going to do a quick recap of the necessary theoretical concepts. First of all, what is clustering? Given a set of data or observation, clustering is a technique which finds natural group within the data or observations, right? The groups should possess certain characteristics. So if you look at this particular diagram, okay, so these individual circles actually represents one data point or observations. And you can see that there are three natural groups or clusters. Now, within the cluster, the observation should be very close to each other. Okay, so this you call as inter-cluster distances should be minimized, right? And you want this cluster to be as far away from each other, right? So that objective or that characteristic you call as inter-cluster distances are maximized. So this property of togetherness within a cluster is also called as cohesion. And this property of the clusters being far away from each other is called as separability. Okay. One characteristic of this clustering is the definition is ambiguous because we said natural groups. So let's look at an example. So if we look at this particular diagram and pose you this question that how many clusters are there? So some of you may readily say that there are two clusters, okay, both marked by different colors, right? But if you maybe look more closely, you might convince yourselves and no, there are smaller clusters, right? So actually there are 6 clusters, okay? And then you might be just skeptic and think that here these two clusters and here these two clusters are closer to each other. So they should be merged, right? And you can say that there are 4 clusters. So this ambiguity actually makes the clustering algorithm much worth for studying. Now let's look at type of clustering. Okay. So there are several ways to actually, divide the clustering algorithms. But we look at one way where we say one set as hierarchical clustering and another set as partitional clustering. So if you look at this particular diagram and these individual blue circles are observations, then partitional clustering actually partitions all the observations. Okay. So these are different partitions and they are non-overlapping. Okay. So K-means is a partitional clustering algorithm. Whereas in a hierarchical clustering algorithm, you see that you have figured out these two clusters are close to each other and can be thought to be part of this bigger cluster, right? And finally, this cluster and this cluster is part of the overall cluster. So the ambiguity that may be little lesser when we are dealing with the hierarchical clustering. Okay. Now let's look at some of the use cases. So any business you take, maybe healthcare, maybe insurance, retail, telecom, you always want to know your customer better, right? You want to profile your customer. You want to segment your customer. Why do you want to do that? So that, okay, this customer group actually belongs to senior citizen and these are your teen group. So their requirements are different. The product that I'm offering to this set, the senior citizen, will be quite different from what I want to offer to the teen group, right? So that's the reason you do a segmentation. Another application area is fraud detection, okay? So basically there is also one technique of clustering which is called as density based clustering. Density based clustering simply means that the points are very close to each other, okay? And if you find some clusters, like, if you look at this example, this cluster, this point is actually quite away from the majority of the points, right? So this point can actually represent an anomaly, and that anomaly can be a fraudulent transaction in case of business transaction. The same analogy can be extended to fake news detection and intrusion detection problems, okay? Another problem is called as optimized portfolio. So if you want to have a good portfolio, you want to minimize the risk. How can you minimize the risk? More diversified portfolio you have, your risk is minimized, right? So essentially, if you cluster, different shares or different investment instruments, right? You want to take investment instruments from different cluster. That will make your portfolio more diversified. Okay. Now let's go and look at how K-means work. So K means, right? So K means has two terms. One is K. K stands for how many clusters you want. So that is an input you need to give to the algorithm. And why do you give a means? So this means is required so that every time you can find out center of a cluster. More when we discuss it. So let's say, these are some of your points, right? And what you initially do is, if it is given that K equal to 3, then you randomly pick out 3 observations randomly. So here in this problem, we have picked these 3, but this could have been any 3. Okay. After that, what you do is, you take each observation and find out the distance between this observation with all the 3 clusters, right? So these are also called as centroids. Okay. And wherever the distance is smaller, so like in this case, this particular observation will be closest to this. So I will say this belongs to this cluster, this red cluster. For this one, the distance with the green cluster is lowest. So I'll put it in the green cluster. And maybe this one, it is closest to the blue cluster, and I will put it to the blue cluster. So that's how, this has been marked. So once this assignment has been done in step 2, what you do is, you calculate the centroid. So earlier, these 3 points were representing as centroid or representative of the cluster. Now, what you are going to do is, you are going to take arithmetic mean of this 2 points, arithmetic mean of these 7 points, and calculate respective cluster centers. So as you are using this arithmetic mean, so therefrom this means term is propagating to K means, and you calculate the centers, and then you again repeat the process, right? So if now the center is somewhere here, for each of the points, again I find out the distance from each of the clusters, right? And I do the assignment. So finally, I might get a set of cluster like this. So a algorithm stops or terminates when we say that it has reached convergence, right? So this is a concept which is very different from one algorithm to another. Where I can say K-means has converged. So when there is a movement from one cluster to another cluster, like in this case, some of the observation has moved from one cluster to another cluster, right? So this one, if you see, has finally moved, or this one actually has finally moved to another cluster, right? So this you call as migration. When the migration stables, right? So the iterations, you are running the iteration, but no change is happening in the cluster assignment and the cluster centroid, then you say the algorithm has converged. Now let's see how we can apply that or use that in R. So we are going to use a very simple data set called as HSAL. Okay, so let me just run this. Okay, and I have plotted it, but nonetheless, let me also show the data set. It is very small. It has just got 14 observations, okay, and 2 columns, which is age and salary. So you can consider that these are different customers. You know their age and their salary, okay. And initially, what you want to do is, you just want to do a scatter plot. So if you look at the data and try to interpret, so this is also a very, very important thing, because when you are dealing with business, you cannot create a cluster and take that to them. You also need to interpret the cluster. You also need to give them the semantics of the cluster. So if I just look at the plot, I will see that, okay, here I see that there is a senior citizen group, right, post retirement, and of course the take home or their monthly income is quite low. And I also see that there are some people who are probably early career, okay, maybe also up to this, who also have a moderate amount of salary. Mid career people, there is quite an increase in the salary. So if I think of semantics, right? If I think of semantics, these are my three clusters. Why it is important? So when I will create my clusters, I would like to validate that whatever was my understanding, are the clusters also giving the same groups. Okay, all right. So these are some of the parameters that k-means takes. So x is the data. Center simply tells you that how many centers you want, right? For how many iteration you want to run that. And this is also a very important parameter, n start. So essentially, n start tells you that how many different random initialization by which you can start. So you understood that in k-means, we choose the first k points randomly. So if I run k-means another time, it will pick different points, and as a result, the clusters can be different. So for that, what you can do is, for different random selections, you get the clusters and you report the base cluster. Okay. So let us run this. Okay, and what we are essentially doing over here is, we have applied k-means on this data. We have said that there are three clusters and we are starting with 5 random points. And these output we have stored in this variable. So this is a variable name. You can have variable name of your own. Okay. And what we are going to do is, we are going to plot it again and color them by different clusters. So if they are from the same cluster, they will be having the same color. Do you agree with the cluster formation? No. What has happened is, you see that if the salary is less than 40,000, then it is in one cluster. If the salary is maybe between 40,000 to 85,000, then it is another cluster. And if it is more than 85,000, then it is another cluster. So what has essentially happened? The salary attribute actually has dominated the age attribute, because look at the range of the value, right? So any distance based algorithm, this is a problem. So for that, what we'll do is, we'll scale it. Why do we scale? So that all variables are in equal range. Okay. Before that, what we can do is, we can look at some of the properties of this k-mount. Okay. So let's look at this. So it will tell you a lot of things about the clustering that you have done. It will tell you, the cluster size. It will tell you the cluster centers. So these are your representative points, the centers, right? It will also give you a clustering vector, which tells you that, this is in second cluster, this is first cluster, third cluster. And it also gives you certain measures, what we discussed about those separability and cohesion. Another thing is that, for going to this, below level, so you'll see that there are some available components here. So if you want to look at that, what you can do is, you can just km.out is your original variable. So if you just put a $sign, okay, and press tab, so it will give you several options. Okay. And so if you want to look at individual centers, so you can put that and run this, and you can look at the centers. We are more interested at those separability and cohesion related metrics. So for that, I will introduce you with another term, which is called as within SS. At least that is what is referred by our terminology. So let's say these are your three clusters, right? And these asterisks, these yellow stars, actually represent the cluster centroids. So what we are doing over here is, we'll find out the distance of all the points from the centroid for each of the point, right? So I'll get a value for this cluster, and I will take an average of that, right? So that will be the within cluster sum of squares for this cluster. And there is another measure which is called as total within sum of square, which will be sum of all the three clusters. Now, can you quickly tell me that should this within cluster sum of square be small or large? So you can understand, if they should be close to each other, they should be small, right? So this WSS, okay, so WSS should be as small as possible for a better quality cluster, right? However, there is a catch. So if you get too charged up, right, too carried away, and create as many clusters or as many cluster as there are observation, then this within cluster sum of square WCSS will be actually 0, right? But do you want that? Is that a good scenario? No. So for that, what we do is we take help of something called as an elbow plot. Okay, something called as an elbow plot. So essentially, it tells you that how many clusters you should use. Okay, so let's actually run this. Now we are going to run on not this small data set, but we are going to run for the iris data set. You already know about this iris data set. So I can quickly give you a glimpse. So iris is loaded, okay, and if you just look at it, so the data will be something like this, okay. So it is just taking little bit of time. Yeah, so you see that, this is your sepal length, sepal width, petal length, petal width. So there are three categories of flowers and their corresponding four attributes, okay. So this is a very standard hello world data set. Many of you have already seen it. So what I'm going to do is I'm going to ignore this attribute, which is actually the flower attribute. I'm going to use the first four columns. So one column 4 actually tells you that we are taking the first four columns, and we are going to take a vector, initialize it by this, and then we are going to run a loop from 2 to 10, okay, and we are going to store this total within sum of square. So why we are doing that? Because we want to find out that if we are using number of value of k as 2, what is the total within sum of square, and if we are using 3, what is the total within sum of square. Now it is a monotonic function, okay. So as we increase the number of cluster centers, this total within sum of square actually goes down. So we want to stop at where there is a significant drop forming kind of an elbow, okay. So let us run it, okay. So what is happening is actually k-means is being run for this 9 times, okay. And if you say this, so this is how the plot is, and you can clearly see that the biggest drop has happened between 2 to 3, right? So this is where you have the most prominent elbow, okay. And eventually you also knew that there are three groups, okay, three type of flowers. So this is actually confirmed by the elbow plot that you have plotted, okay. Now, we were discussing about one problem, right? We saw that our clustering went for a toss because the age and salary had different scale. So what we can do for that case? We can scale the data frame. Okay, we can scale the data frame and then run the k-means algorithm. Okay, so this data frame we are calling as df1, and now in k-means we are using this scale data frame. So now if you run this, you see now the clusters are much better formed. So this is now separated, this is separated, and this is separated. So that is the impact of scaling. These are small design issues which are very important for your algorithm to give better or correct result. Now let's come to hierarchical clustering. Let's first understand how it works. So there are actually two types. One is called as agglomerative, another is called as divisive. So we are going to focus on agglomerative clustering. So what we do there is we see that which two observations are close to each other and we agglomerate them or merge them. Like, these are 6 points. So first we have seen that A, B and D and E are equidistant and closest to each other. So we have put them in one cluster. Next we have find out that which one is closer to this cluster or these new formed units, okay. And that's how we have merge ABC and then DEF and then the final cluster, okay. And we represent this distance using a diagram like this, okay, which is called as dendrogram. So this is quite an important visualization as far as hierarchical clustering is concerned. There is one important issue though, okay, that when we are trying to, I can understand that when I am finding the distance between A and B, I can find the distance. But what if I want to find out the distance between this cluster and this cluster? So one possibility can be I can find out the distance between B and D. Another possibility can be I can find the distance between A and E, right? So all these actually form different option named as single link, okay, complete link. So in single link, what happens is, as I said, you look at the minimum distance, okay. In complete link, you look at the maximum distance. In average link, you actually look at, you find out the distance between all the points and take the average. And in centroid distance, you find the centroid of the clusters and take the distance, right? So when you use that in R, you will see that there is an option like method equal to complete. So you can use different methods over here, right? So if I quickly want to show you this, okay, so let me take a code block, and if I do a Hclust, right, then you will see, all right, it is not Hclust, it is Hclust, okay. So you'll see that in methods you can use different type of methods that are there, okay. So all these methods you can try out, and actually your agglomerative clustering is not actually one clustering but a family of clustering algorithms. So this is one of the advantages. Now there is one more thing. The D that we were using here, this is actually a distance metric, okay. And once we run this on the same set of data over here, right, so let me just run this. So what we are doing is, we applied something, a function called as dist on this scale data frame, and we have mentioned that method equal to complete, and then we are actually plotting the data using the dendrogram. Why this cut tree is required? Because this gives a dendrogram, not the final clusters, right? So you can use some distance measure and can break them into clusters. So let me run this, and when I run this, we'll get something like this, right? So we know that, okay, 6 and 10 are closer, 5 and 9 and closer, and so on and so forth, right? So one other important thing I want you to look at is about this distance, okay. So look at what distance does, right? So if you look at actually distance, you will see that there are many distances that are available. Like you have Euclidean, you have maximum, you have Manhattan, Canberra, binary, Minkowski, and so on and so forth. Not only that, you can have your own custom distance measure, prepare the distance matrix, and you can give that as an input. And you can quickly also want to look at distance of df1, okay. So look at how the result will be, right? So this is actually, as it is a symmetric metric, okay, so you don't have this entries. This just tells you that 1 and 2 has this much Euclidean distance, and so on and so forth. Okay, so I hope you could learn something from today's session. Okay, we'll look forward to interact with you. Please, like this video. Please subscribe to our channel. Please put your question on our comment section. Okay, thanks guys. Take care.